Hi everybody. This video here is going to introduce a couple of functions to you. We're calling them cosh and sinh. That's kind of an informal name. Their formal name really for the cosh is actually called hyperbolic cosine, and the other one, the sinh function there, is called the hyperbolic sine. So these are very interesting functions. This video will just be kind of a basic introduction to these two functions. And then I'll also talk a little bit about why they're called this hyperbolic cosine and hyperbolic sine. Because when you look at the equations, you don't see hyperbolas and you don't see trigonometry either. So it's kind of weird that they're called what they are. So I'll try to touch upon that a little bit as a way of explaining. So let's look at first at the hyperbolic cosine function. And you see the equation there. It is defined as, we say cosh of x. The hyperbolic cosine function is e to the x plus e to the negative x over 2. And I wanted to introduce this function to you in kind of an interesting way. That is, I'm going to show you how the graph of this is obtained by graphical addition. That is, adding graphs together. The two graphs that I'm going to add are basically the parts of that cosh function. So e to the x over 2 plus e to the negative x over 2. And if you look at those two graphs and thought about adding them together, I'll show you what that means here. So first off, e to the x over 2 looks like that. It's kind of a basic exponential growth function using base e. So that's what it looks like there. The e to the negative x is a reflection across the y-axis, and it looks like that. So there's our two functions, symmetrical across the y-axis there. And when I say I'm adding them together, when you add graphs together, what you're really doing is you're adding up the y values for corresponding x values. So let's say we take the x value right there at 0. All right? So in other words, the y-intercept of those two graphs. Well, they happen to have the same y-intercept. So if I add that number to itself, okay, I add the y-intercept of one plus the y-intercept of the other one, I'm going to get the y-intercept of our new function, which is just twice as much. So it happens that both of those exponential functions have a y-intercept of 1/2. So when you add them together, you get a y-intercept on your cosh function of 1. So that's our first point on the cosh function right there, the y-intercept. And if I took another point, let's say over here to the left of the y-axis, and I took the y value of the blue curve, and I added to it the y value of the yellow curve, so it's just a little bit above that blue curve, that would be another point on the cosh function, okay, for that negative x value. And if I took the positive x value over there, did the same kind of thing, that is, I take the y value on the yellow curve and I add to that the y value on the blue curve, I get another y value on my cosh function. And if I just kept doing that, you would see that this cosh function, the green one, follows along that yellow curve, just getting closer and closer to it. Why is it getting closer and closer? Well, it's because the value that I'm adding from the blue curve is getting smaller and smaller. I'm still adding something, but that difference is now getting less and less. So the green curve is getting closer and closer to the yellow curve. All right, and you could probably logically come up with why in the same way the left-hand side of that curve follows the blue curve as it goes upwards, just getting closer and closer to it because the value that we're adding is less and less. So that's what the cosh function looks like. There's just kind of a crummy hand-drawn shape of it. Here's a better image from a graphing calculator, and you can see there's the two dotted lines being the exponential curves, and our cosh function right there is the sum of those two curves. It looks like a big letter U right there. Okay, so that's the hyperbolic cosine function. Let's take a look at the hyperbolic sine function, and its definition, or its equation I should say, is very similar to the cosh function, but one slight difference, e to the x minus e to the negative x over 2. Okay, so if we did the same kind of graphical addition, that is kind of splitting that function up into two functions and adding them together, which is an interesting idea, I think, they look like this. So it's e to the x over 2 plus negative e to the negative x over 2. So if we graph that, there's our e to the x over 2 again, same thing as before. Now the negative e to the negative x, well, that's like a double reflection. That's a reflection across the x-axis, that's that first negative sign, negative e on the base, and then the exponent, negative x, means a reflection across the y-axis. So that double reflection kind of looks like that. Okay? So when you add those two curves together, and I won't go through too much detail about that, but when you add them together, you get a curve that's kind of like that, in between them. And it's kind of, it looks sort of like x cubed, or maybe it looks kind of like the tangent function. But that's what it looks like. Here's a better image off of a graphing calculator there, so you get a better picture of what that graph looks like. All right, so that's just a basic introduction to those two interesting functions, hyperbolic cosine and hyperbolic sine. And strangely enough, they're both actually exponential functions. So how do we get from exponential functions, or how do we get an exponential function from something called a hyperbolic sine or a hyperbolic cosine? So the word hyperbolic refers to a hyperbola. So it must have something to do with a hyperbola. And sine and cosine, okay. Well, let's take a look at our basic sine and cosine. If you recall, from your exposure so far, you've seen some sine and cosine functions, and they were always based on a circle. In fact, this point on a circle, which sweeps out a certain angle, we take a look at the vertical distance away from the center of that circle, and we call it the sine of theta, and the horizontal distance away from the circle, and we call it the cosine of theta. So there's sine and cosine based on a circle, and in fact, the trigonometric functions that you are familiar with, they actually are often called circular trig functions. Okay, and the equation of that circle, as you may recall, is x squared plus y squared equals 1. Well, this is very interesting. A circle is actually a very ancient form, and it's part of a group of forms known as conic sections. Well, another one of those equally ancient forms and conic sections is a hyperbola. It looks like that. All right, totally different looking shape, but having the same sort of heritage as a circle. And in fact, the equation is very similar as well. And so there's the center right there at the origin for this hyperbola. And if we thought of a point on the hyperbola and its vertical distance away from that center as the hyperbolic sine, and the horizontal distance away as the hyperbolic cosine, we can do all this kind of trigonometry stuff that we were doing with circular functions, only we can now base them to represent points on a hyperbola. Okay, and so in the same way that we could combine sine and cosine and get tangent, that is sine divided by cosine is tangent, and other manipulations of circular trigonometric functions, we can do most of that same kind of thing with manipulating these hyperbolic sine and cosine functions. And quite honestly, we're not going to get too detailed about that. We're going to spend a little bit more time in working with these. I think you'll find it fairly easy to do and very interesting. Something new for your course this year. Anyway, just to thought I'd follow this up here, the equation of that hyperbola is x squared minus y squared equals 1. So it's very similar to the equation for a circle, but it looks very different. And so the algebra that sort of connects these shapes with the exponential functions for cosh and sinh is very interesting. I'm not going to go into it here, but I encourage you to explore and look into this topic. I think you'll find it very rewarding. Anyway, I hope you enjoyed that. I'm very glad that you watched, and be well, and please do some more good math. Bye-bye.